So let's talk about trig functions of a unit circle. Now, there are two approaches to trigonometry in general. One is a right triangle approach, which I'm sure, again, most, if not all of you already are aware of it. That's when you form the right triangle, and we will do this, by the way, later on, maybe. But for now, we are not doing it. But here's how most of you probably know this. When you have these sides of an angle, right? And you define sine, cosine, tangent, and so on as a ratio of sides of a triangle. For example, sine would be the ratio of the angle theta. Sine of the angle theta is the ratio of opposite to hypotenuse, and so on and so forth. Well, that's one approach to trigonometry. The other approach is called the unit circle approach to presenting trig functions. Now, when we use a unit circle, there is no angle actually. There are no angles to tell you about. So we just think about in terms of coordinates of a point on a circle. You think of these trig functions, sine, cosine, and so on, as coordinates of a point on a unit circle. So here what I have is a unit circle. Okay, now the unit circle, let's go back to our description of what a unit circle is. A unit circle is simply a circle of radius 1 whose center is at 0, 0. So this is the equation of the circle that you see on the right side. Now, because it's called unit, a unit means the radius is 1. So the distance from the center out to any point on this circle, this distance is 1 unit. Okay, and that's what you're seeing here. The coordinates of this point, therefore, is 1, 0. The coordinates of the point here is 0, 1. The coordinates of this point, negative 1, 0. And the coordinates down here, 0, negative 1. You see that? Therefore, we have those coordinates. Now, if I choose, let's say I have, if I draw a line here, tangent to the circle, okay, the length of this line, okay, is going to be, let's say, t, whatever t is, a positive value. So whatever that length is, and imagine if we bend this line and kind of place it on the circle now. Okay, so if I could somehow bend it and place it on the circle, let's say because of the curvature of that circle, so this is what that line t of length t would look like now, wouldn't it? Right? Again, imagine if you just somehow could fold it, bend it, and place it there. Therefore, corresponding to the length of this line, which now is arc length, is a point P whose coordinates are x, y. And x, y, we can see it here. That's the x and that is the y. Whatever those are, looks like a 0.6 and 0.8, something like that, whatever that is. But here, what's important is that we can represent a point on the unit circle that corresponds to t. Let me write that. So here, P is a point on the unit circle. Okay, and it's a point that corresponds to t. Unit circle, let's also add that, corresponding to t, the real number t. Notice again, there's no angles here. I haven't formed any angle theta here. All right. Now, we can define, and t here, by the way, is a real number. T is an element of a set of real numbers. Could be positive, negative, 0, whatever. Now, we can define these functions. We're going to define sine function to be the y coordinate. Sine is the y coordinate of that point P. Coordinate of P. We're going to define cosine function to be the x coordinate of point P. All right, so in other words, right in here, this is x and this is y. So x is going to be cosine of t, y is going to be sine t. Isn't that cool? And there you have it. So no angles. Again, I want to emphasize we're not working with any angles here. Okay, so that's all we have, just the coordinates. Now, what do we want to define next? Well, if x isn't 0, if we don't let x to be 0, then we can actually define a third trig function, tangent. The tangent function, call it tan of t, and it's the ratio of y to x. Now sine, let me write these. Sine of t, therefore, is y. Cosine of t is going to be x. All right. Now, if y isn't 0, I can divide by y, and we get cotangent. Cotangent, that's cotan t, is going to be the ratio of x to y. Okay, and again, if y isn't 0, I can define secant as the following. Secant of t is going to be 1 over x, and I'm sorry, y. So let's say x, if x can't be 0, because I'm dividing by x. And if y isn't 0, then cosecant, which I can write as C for cosecant. Cosecant of t is going to be 1 over y. All right, so there you go. Again, I want to emphasize there is no angle theta here. So we're defining trig functions as functions of as real numbers. Okay, these trig functions are functions of real numbers. All right, so let's see how this is going to work out. Let me copy my circle and we'll do some examples here. All right, so here I have copied again my unit circle, and suppose we want to find the 6 trig functions of real number t, where point P again here on the unit circle corresponds to t. Well, the point I've selected is -1/2 and square root of 3 over 2. So that means x is -1/2, and because the point is on the circle, so that's going to be the y value because it's positive. So I go up until it touches the circle at that point. And there you have it. This is what point P is. Now remember the coordinates, the first number is going to be cosine of t and the second number is going to be sine t. So as an ordered pair, therefore, we see if it's on a unit circle, then we can label these as cosine and sine t, right? All the coordinates likewise. So this would be cosine t, sine t. All of them. This one is cosine t, sine t, and we are actually looking at now the trig measures of real number t for different values of t. Like here, for example, t is 0. When t is 0, cosine of 0, cosine of t, and t is 0. You see we have just a point on the circle. Then the cosine of 0 is 1, sine of 0 is 0. You see how that works? Very easy. We don't have an angle here. So I'm just going to write these. Therefore, cosine of t. Oh, and where is t here? T is indeed right in here. If I just go along the arc of a circle, there you go. That is what t is right there. T is the arc length, starts from 1, 0 and ends at p. That's what t is. So cosine of the real number t is going to be -1/2. Sine t is going to be √3 over 2. Let's do tangent, tan t, and those ratios, we define them up here, right? We defined tangent, cotan, secant, cosecant as ratio of either x by y, y by x, 1 over x, or 1 over y. So tangent of t is going to be the ratio of y to x. Well, y is √3 over 2 divided by x is -1/2. That's -√3. What about cotan? Cotan is a ratio of x to y, the x component to y component, so that's negative a half divided by root 3 over 2, which is negative 1 over root 3. And we can rationalize this. Usually they rationalize the denominator, so we get negative root 3 over 3 after it's rationalized. Okay, and what about secant? Well, secant of t, that was the ratio 1 over x, right? Which is 1 over negative 1/2 or negative 2. What about cosecant? Cosecant t is 1 over y, and that's 1 over y was root 3 over 2, so that's 2 over root 3, which again we rationalize as 2 root 3 divided by 3. All right, and there we go. Those are the 6 trig functions corresponding to a point on the unit circle. All right. Now, so that's all that is. And well, let's now talk about trig functions of angles. So now is the first time we're going to talk about angles. Let me actually write that. We're looking at trig functions of angles now. So we're going to somehow now bring in to this or incorporate angles along with our coordinates of a point on the number line. Okay, so let me bring my unit circle up again. Okay, so here's my unit circle again. So what I've done is I've actually plotted some points here on my unit circle. So here's 1 0 0 1 negative 1 0 0 negative 1. Those are the coordinates at those points. And what I've done is I've just marked an arc of a circle. Remember the real number t, arc of a circle of some length t. And remember the arc length notation we used in previous lecture was s, corresponding to a point p, coordinates xy. Now this is a unit circle, right? So that means the radius is 1. Therefore, if the radius is 1, the formula we had from previous lecture is that the arc length is given by s equal r times the measure of central angle theta. Well, r is 1 here, right? Because this is a unit circle. So only for a unit circle, s is equal to 1 times theta, and s is equal to theta. So what we're saying is that the measure in radians, real numbers, of the central angle theta and the arc length are exactly the same. Okay, and that is only true for a unit circle. All right, and if that's true, then here's what we can do. Remember, t and s are the same. Therefore, from this, I get theta is equal to t. Well, that's nice. That means I can say that sine of t, remember t is the arc length that corresponds with a point on the circle, p. So I can say sine of t is equal to sine of theta. But again, this is for a unit circle, folks. I want to emphasize that. Now, and keep in mind, t was a real number, right? A real number. Here, theta is a measure of an angle, and to keep it real, theta must be in radians here, right? That's why theta equal t. And now we can actually convert all of the trig functions, all 6 of them, instead of t, to the measure of central angle theta, which is more familiar to everyone. So tan t become tan theta, and so on and so forth. Cotan t would be cotan of the central angle theta. Secant t becomes secant of theta, and cosecant of t becomes cosecant of theta. All right, and there we have that. So now we have functions of real numbers t, or trig functions as functions of angles. Now, in either case, we simply call these trig functions. Whether they're functions of real number t or central angle theta in radians, we simply call these trig functions. Okay, Now that we've defined trig functions in terms of angle theta, let's actually do this. In this example now, let's say we want to find the trig functions of, and we're going to go with these special angles now, 0, 90, and then I'm going to go 180, 270, and 360 degrees. Okay, now something special about these angles. If you look at these angles, every one of them lies either on the x or the y axis. Okay, so let me bring my unit circle up again and I'll explain what I mean. Alright, so for the measure of angle 0, when theta is 0 degrees, we're right in here, right? That means the initial terminal side of theta are there. So for theta equal to 0, cosine of 0 now, okay, 0, and we're doing in radians, by the way. Okay, I know, here's the thing, the 0 degrees is equivalent to 0 radians. They both look like 0, right? But this is actually in radians that I'm using, corresponding to 0 degrees. For the other ones, I will convert them to radians, and you see the difference, what I mean here. All right, so for cosine of 0, remember the first number is going to be therefore cosine of theta. The second number is going to be sine theta now. Therefore, cosine of 0 is 1, and sine of 0 radians is 0. And once you have this is your x and y, correct? These are your x and y at that point. Now you can get your tangent, cotan, and all that. So let's do tan of 0 radians or 0 degrees, because they're equivalent, is going to be a ratio of, again, y to x, right? Tangent is ratio y to x. So that means I'm going to divide y is 0, 0 over 1 is 0. There's tangent. Cotangent of 0 is going to be x to y, 1 over 0, which is undefined, division by 0 undefined. Secant of 0, secant is going to be 1 over x, and that's 1 over 1 or 1. Cosecant of 0 is going to be 1 over y, and that's 1 over 0, and it is again undefined. Okay, you see how we can quickly determine those. You don't need a calculator, and you don't really need to memorize any of these. Now these usually, by the way, what happens is this, we derive or find out the trig function for sine and cosine directly from the circle, and then for the other 4, because they're made up of some ratio involving x and y, either or both, then we just get those from sine and cosine. Okay, so for these other ones, I'm just going to do sine, cosine. Likewise, you can do all the trig functions. You can do the other 4, tan, cotan, secant, cosecant, and verify it. But let's do it for theta 90 degrees. Now 90 degrees, if I convert degrees to radian times pi over 180, that's going to be pi over 2, right? It's going to be pi over 2 radians. Therefore, I can do this. I can say that cosine of 90 degrees is equivalent to cosine of pi over 2. See, these are different. One is degrees, the other one is a real number. That's what I was referring to, the zeros. Now, hopefully up here, the 0 makes sense. One is real, the other one is a degree measure. Okay, so for cosine of 90 degrees, now we have moved to 90 degrees. Remember, first component is cosine, second is sine. So cosine of 90 is 0, sine of 90 is 1. And you can get the other 4 from these. All right, let's do it for theta equal 180 degrees. And these angles, by the way, 0, 90, 180, 270, and go back to complete this rotation or revolution at 360. These are what we call quadrantal angles because they lie on the borderline of two quadrants. So for example, 0 degrees separates Q1 from Q4, right? The fourth quadrant. So that's why it's called quadrantal angle. The quadrantal angles lie on the X or Y axis. So 180 degrees, therefore sine of 180 degrees, which is the same as pi, is going to be 0. Cosine of 180 degrees is going to be -1. See that? How easy it is? There is no triangle here, folks. It's just coordinates of points on the circle. For 270 degrees, sine of 270 is the y component, which is -1. And cosine of 270 degrees is the x component, which is 0. And finally, for 360 degrees. And I'm leaving the other 4 measures, tan, cotan, secant, cosecant. For you, you can do them this way, right? Right up here. Because these are simply the ratio. See, right in here we have the ratios. So you can just plug in for x and y. Some of them are going to be for quadrantal angles. Some of them are going to be undefined. The other one is going to be 1. So it's either 0, 1, or undefined. Or it could be -1, depending on where you are. Okay, so for cosine 270 degrees, we did it. 360 degrees, you're back in here. Therefore, cosine of 360 degrees is the x, and sine of 360 degrees is the y component. And there you have it. And again, I want to emphasize that you don't need to memorize these. You simply do these by working them off of the circle. All right. Now, let's take a look at others. Now, let's do this also. We just finished it for quadrantal angles. Let's do this for some special angles. And throughout the course here, by the way, and on your future courses and math courses, we tend to stay with these special values for the angles. So let's say next we're going to look at theta, where theta is 30 degrees, 45 degrees, and 60 degrees. So all in all, we'll have all the trig measures for all quadrantal angles as well as all of these special angles, 30, 45, 60. So let's begin with our 30 degree angle. So for our 30 degree angle, this is kind of how the 30 degrees is going to look like. Right in there. Okay, so suppose that's 30 degrees. Okay. So here's the measure of angle, theta equal 30 degrees. All right, now I need to find the coordinates of this point, right? That corresponds to the angle theta 30 degrees. Now the coordinates of the point, because this is a triangle, I can form a triangle here. And then I can use the knowledge of trigonometry, right? From geometry, not trigonometry. From geometry, this is what we know from geometry, that the side opposite the 30 degree angle is 1/2 the hypotenuse. So if the hypotenuse is 1, this is 1/2. And then we also know about the Pythagorean theorem, right? From the Pythagorean theorem, we know that if you take the square of the hypotenuse, that should equal to the square, some square of the other two sides, called this y. So from this, y turns out to be 1 minus 1/4 or 3/4. Oh, that's y squared. So y would be square root of 3/2. So that's what we know from, again, geometry, not trigonometry, but geometry. So that's what I'm going to do therefore. The y value here is going to be 1/2. The x value from here to here, x value is going to be root 3/2, and the hypotenuse is the radius of a circle is 1. So if you note now, I have the coordinates of this point, therefore. And another thing I can do is using unit circle, I can also write x squared plus y squared equal 1. And x squared is equal to, we mentioned that side opposite 30 is half the hypotenuse, so that's going to be 1/2. That's the y value here. 1/2 square it and equals 1. So x squared is going to be 1 minus 1/4, and x would be root 3 divided by 2, exactly like this part does. Here, there's sum of square equal, again, square the hypotenuse, but the hypotenuse is 1. So there you get it. Very similar to what we just did here. And this is the derivation from geometry. All right, the key is that I have the coordinates of the point now. So I can write these coordinates as root 3 over 2 and 1/2. And once I have that, then I can write all the trig functions of a 30-degree angle. So sine of 30 degrees, which in radians is going to be sine of, let's see, in radian, 30 times pi over 180 is going to be pi over 6. Okay, so sine of pi over 6, that's going to be the y component. The y component is 1/2, right? And cosine of 30 is going to be the x component of that point on the unit circle, which is root 3 over 2. See that? Again, we don't have to memorize these. You can always create them on demand as you need them. I really want you to memorize these, because if you memorize, then you're bound to forget. So at least you stand better chance of remembering these a little longer. And then from this, you can do tan, cotan, everything that follows from it. Again, all we need to know is really sine, cosine, and you can derive the other 4 trig functions. Now, what about for a 45 degrees? Let's do this for the 45 degrees. So I'm just gonna bring my circle up now for a 45-degree angle. All right, so let's do this now for the 45 degrees. We're done for the 30 degrees. Again, I'm leaving the other 4 trig functions for you to kind of explore for yourself. Let's do this for 45 degrees. So what if theta is 45 degrees? Well, now the geometry of this, if you have 45 degrees, that means the triangle that I'm forming here is going to be an isosceles triangle. The measure of this angle is going to be 45 degrees. Therefore, the sides are equal, so x and y are the same. Now, in equation of a unit circle, we have x squared y squared equal 1. But then if x and y are the same in the case of a 45 degree, I'm going to change my y to x. And I get 2x squared is equal to 1, from which I get x squared is 1/2. Therefore, x is going to be plus or minus 1 over square root of 2, which you can rationalize. You get root 2 over root 2, and that's plus minus root 2 over 2. Okay, now because we are in the first quadrant, we know x is positive and so is y. Therefore, we're going to discard the negative value. And we're going to only accept the positive value. Therefore, x is root 2 over 2. Or 1 over root 2. And because x and y are the same, therefore, this is equal to y as well. Cool. And we have the following. Therefore, sine of 45 degrees, which in radians would be pi over 4, is equal to cosine of pi over 4, as suggested by that equation. And they're each root 2 over 2. And again, from this, we can do tan, cotan, secant, cosecant. All right. Next, take a look at the 60 degrees. So I'm going to bring up my unit circle first. And there we have my unit circle. And let me move this away for now. Okay. So I have my unit circle here, and the measure of the angle here is 60 degrees. If I drop the perpendicular on the x-axis, this angle is 30 degrees. Now, remember the hypotenuse is 1 because this is a unit circle. And what else? Oh, from geometry again, we have a 30, 60, 90 triangle. The side opposite 30 is half the hypotenuse. So the opposite side measures 1/2, and therefore this side is √3/2. We can derive that side from Pythagorean theorem. Now let's do the trig measures for 60 degrees. 60 degrees, that's going to be pi/3. When you do 60 times pi divided by 180, that's what you're going to get. So the trig measures of this sine of pi/3 is going to be the ratio of, remember sine is the ratio of, or the second component, sorry, sine is just y, which is √3/2. Cosine of pi/3 is the x component, which is 1/2, and there you have it. And you can do tan, cotan, secant, cosecant from those. All right. Now, once you do, then here's what I can summarize everything. Usually you're given this circle, and now hopefully we can follow along and see where these numbers come from. First of all, these are the quadrantal angles. See, for 0 and 2 pi, we have 1, 0. And if you want further, we can actually label this as cosine of theta, comma, sine theta for the coordinates of the points on the unit circle. All right, and this is a unit circle because you can see the distance from here to here is 1. So this is a unit circle that you're looking at right now. For 30 degrees, we derived each of these, right? We derived them. Now, for the other quadrants, we can actually use symmetry to do this. So, for example, let's say for 30 degrees, and then reflected, the coordinates of the point here, which corresponds to degree measure of, or the radian measure 5 pi/6, are going to be negative √3/2 and 1/2. So we can simply get the others through reflection of these points. Okay, by reflection of them, we can get the exact values for other special angles. All right, and there you have it. So we have the complete unit circle labeled with coordinates. Again, every one of these coordinates is a sine or a cosine for some of these special angles, which is quite a few of them. Right, we have quite a few special angles now. You have 30, 45, 60, and then you have multiples of those, which are these. Right, these are the multiples of 30, 45, and 60. The rest of them are quadrantal angles. So let's take a look at, now I'm just going to spend our time trying to work some examples here. Okay, so let's say in the example I'm making up, suppose I have the coordinates of a point are -1/5 and 2√6/5. These are the points, coordinates of a point on the unit circle that corresponds to real number t. Now notice, by the way, these points, none of them are here because the circle that you're looking at are only for special angles. What I have done here, this is not a special angle for my example. Okay, but we want to find the exact values of the trig functions. Okay, go find trig functions corresponding to P. Okay, therefore, we're back to T business. What is sine of T? Well, sine of T is going to be the y value, which is 2√6/5. Cosine of T is going to be the x value, right? And that's going to be -1/5. And we can do tangent, tan t, y over x, and so on. It's going to be what? 2 root 6 over 5 divided by negative 1/5. So that's just negative 2 rad 6. Okay. And might as well do cosine. Cosine is going to be x over y for cosine. And that's going to be negative 1/5 divided by 2 rad 6 over 5. So it's negative 1 over 2 rad 6. Now we rationalize it. So this is going to be negative root 6 over 12. Okay. And that was, sorry. I said cotan, I wrote cosine. This is cotan t. All right. And what else we want to do? Let's do secant. Okay, secant is 1 over x. So it's going to be 1 over negative 1/5 or negative 5. Cosecant is 1 over y. So it's 1 over that. It's 1 over 2 root 6 over 5. And notice, by the way, that's 1 over y is sine. So cosecant is 1 over sine. And we'll see these as fundamental identities later. Let's rationalize this. And the answer is going to be 5 root 6 over 12. And it's going to be positive. Okay. Let's do another example. So in this next example, suppose I want to do the following. I want to find the exact value of, let's do a quadrantal angle. Example, let's say we want to find secant of negative pi. Secant of negative pi. Now remember, in our unit circle, that's the key, the unit circle. Negative means you go in a clockwise direction, and therefore this is going to be theta equal negative pi. 180 degrees negative, so you end up at point negative 1, 0. And what is secant? Secant is 1 over x. So it's going to be 1 over negative 1, or the answer is negative 1. See how you work it from the circle. From the circle. No calculators. If you can do this without calculators, folks, you make your lives in calculus series and higher courses a lot easier by leaps and bounds than depending on that calculator for basic stuff. And a lot of instructors don't allow calculators for this anyway. So let's take a look at this work now. We want cosine of negative 3 pi over 2. So in this case, again, here's my unit circle. Negative 3 pi over 2, you go clockwise direction until you land here. Remember, that's 270 degrees. The coordinates of the point are 0, 1. Cosine is the first component, so it's a 0. There you have it, directly from the circle. No work to be shown here. Let's do another example. In this next example, suppose I want to do this now. Let's say I want to evaluate the expression 2 sine of pi over 3, negative 3 tangent of pi over 6. Okay, so if I recall the circle that I had for pi over 3, that's 60 degrees, right? For 60 degrees, this is 60. This x was a half, y was root 3 over 2. So that would be 2 times xy. Sine is the y value. So it's going to be 2 times root 3 over 2, correct? And negative 3. Now tangent of 30 degrees. Well, if I recall again the coordinates of a point for 30 degrees, x was root 3 over 2, y was 1/2, right, for 30 degrees. So tangent is the ratio of y, which is a half, to x root 3 over 2. There's my tangent. And I can simplify this as root 3 negative 3 times 1/2 over root 3 over 2. That's 1 over root 3, which we can rationalize, of course. Correct? Multiply top bottom of 1 over root 3 by root 3. So this is root 3 negative 3 times root 3 over 3. These 3's cross out. So we have root 3 minus root 3. Oh, interesting. 0. So that's the value of that expression. Okay. Notice again, I'm getting these directly from the circle. Let's take a look at another one. What if I want to find the trig functions of, let's say, there we go. I want to find trig functions of negative 14 pi over 3. Negative 14 pi over 3. Well, let's see what that is, first of all, in terms of degrees or even radians. Now, pi over 3 is 60 degrees, so 14 times 60 degrees is the measure of the angle. Negative just means a clockwise rotation, correct? So this is going to be 840 degrees, right? 840 degrees. Remember, a complete revolution around or rotation around the circle is 360. So here's 360. Another 360 makes it 720. If I subtract from 720, which is 2 rotations or revolutions, I get 120 degrees remaining. So what I need to do is this. I'm going to go, so I went 1 revolution, and we went to second revolution. I don't know why this program is doing this. And we go another 120 degrees. This will be the terminal side. So the angle is going to terminate in the third quadrant. And let's see. So what is the geometry? The geometry of the angle at that point. Remember, this is going to be from here to here is 120 degrees, right? From here to here is 120 degrees. 90 of it is right there. So this is 30 degrees. Okay. So that's 30 degrees. Again, this means this angle is 60 degrees. The radius 1, side opposite, 30 is half the half the hypotenuse, which is the radius here. So that's root 3 over 2. Perfect. Now we can do this. So what are the coordinates, therefore, of the point here? The coordinates of this point are going to be, because we are in Q3, the third quadrant, x is going to be negative, right? And so is y. Y is going to be negative. So the coordinates are x, which is negative 1/2, and y negative root 3 over 2. And there you have it. Now, some people go back to this circle. They say, well, wait, when you have the circle, how come you're doing it this way? Why don't you just get it from the circle? There it is. The easy way. Well, I may not have the circle every time, right? Someone may not give me that circle. So I rather derive it this way. I will never forget it. So now let's do this. Therefore, sine of theta is going to be the y component. Y is negative root 3 over 2. Cosine theta is the x component, negative 1/2. And so on and so forth. I might as well finish this one. Tan theta, y over x. So it's negative root 3 over 2 over negative 1/2, which is positive root 3. Negative by negative is positive. What is cotan theta is going to be? Cotan is x over y, which you can see. Cotan is a reciprocal of tangent, right? Again, when we talk about the fundamental identities, we're going to summarize these later. So this is 1 over root 3 now. The 2's cross out. Rationalize. And we get root 3 over 3. Cool. And what about secant? Secant is going to be 1 over x. So that's going to be 1 over negative 1/2 or negative 2. Cosecant is 1 over y. And that's going to be 1 over negative root 3 over 2, which is negative 2 over rad 3. Rationalize. And the answer is negative 2 root 3 over 3. And we have all of the trig functions of that angle. Okay. Now, what if, let's finish this off. So hopefully everybody's okay with this example. Now, what if we don't have a unit circle? In my next example, suppose this time now, I'm going to say a point on terminal side of angle theta. Okay, in standard position. That's important. Our angles are all going to be in standard position. That means the initial side on the x-axis and the terminal side is determined by coordinates of the point P. So theta in standard position is, the terminal side is on 0.5 and negative 12. You see that? Let's say we want to find exact values. Exact values means without the calculators of, let's do it for the 6 trig functions of theta. All right. So how am I going to do this? Well, we're going to have, here's a circle. It's not a unit circle. This is not a unit circle in standard position. So this is x and here's y. The point is x positive, y negative. So that means that point is going to be in here somewhere, right? X is 5, y is negative 12. There you go. That's the point. On terminal side, 5 and negative 12. So this is the initial side of the angle, the initial, and the terminal side is this one. That's the terminal side. All right, so the measure of the angle, we can think of it as, this would be theta, a negative angle, right? Whatever that angle is, I don't really care for it. This point P, by the way, it is on a circle of radius r, isn't it? And we can find the radius of the circle. The general form of a circle centered at 0, 0, radius r is this. So I can actually find the radius of this circle. True? When x is 5, 5 squared. Y is negative 12. Negative 12 squared, that's r squared. That's 25 plus 144. So r squared is 169. Therefore, r is square root of that, or 13. And by the way, r, the radius of a circle, we always take it to be positive. Okay? So this point P is also on a circle of radius 13, centered at 0, 0. Now, if I create my triangle here, so this is x and there's y, and we can do this now. So let's get the measure of cosine. Cosine is going to be now, because this is not a circle of radius 1, so it's not just x. If the radius is different from 1, it's x over r. Okay, so it's going to be 5/13. What about sine theta? Only for a unit circle, it's y. For a circle other than unit circle, you do y over r. So it's going to be negative 12 over 13. Okay. And the others follow. Tangent of theta now is just y over x. So that's going to be negative 12/5. Cotan theta is the reciprocal of that, reciprocal of tan. So that's 5 over negative 12. What about secant? Well, secant is r over x, which is the reciprocal of cosine. So it's going to be 13/5. And cosecant is going to be the reciprocal of sine, r over y, and that's going to be 13 over negative 12. And there you have it. These are the exact values of all 6 trig functions corresponding to angle theta and corresponding to a point on a circle of radius 13, the point 5, negative 12. All right, so hopefully again this is a good review of these 6 trig functions as points on unit circle. And with that, we are done with this lecture. Thank you for watching.